Buenos días, Ariel. Buenos días.
Buenos días, profe.
Buenos días, profe.
¿Sí me escuchan?
Sí,
Probando, probando. 1, 2, 3. Tenía bajo el volumen.
sí se le escucha, profe.
Perfecto.
Ya.
Mientras esperamos a los demás, ¿hay algo que quieran discutir, preguntar? ¿Cómo les va? Es la primera vez que se conectan al curso de semiconductores.
No, profe. Qué mal. O sea, más o menos bien. Ahí llevándole las cosas, pero ya como que un poco, no sé, cuesta mantener una rutina, digamos.
Sí, cambian las cosas todos los días, ¿no? Poco.
Ujú.
¿Y tú dónde estás, Ronald?
Yo en Quito.
En Quito. Okay. ¿Fuiste de los que migraron rápidamente o te quedaste algunos días en Yacha?
O sea, del jueves que fue que ya pararon las clases, me quedé hasta el domingo en Ibarra y de ahí ya regresé porque sí se notaba que se iba a ir de largo.
Claro.
Mejor irme a Quito.
Y el que quiera moverse ahorita se pone difícil. Yo creo que las rutas están interrumpidas totalmente, ¿no?
Sí, espero que están con mucho control varias. O
Claro.
sea, por ejemplo, en todos los peajes espero que haya gente.
Ajá.
Al menos acá en Quito había escuchado eso. No, de todos, sí, da igual. Moverse de provincia a provincia también es complicado.
Ujú.
¿Cómo está el profe?
Yo, tranquilo, la verdad, aquí en Ibarra, digamos, no he tenido muchos problemas. Afortunadamente tenía esta tableta desde la crisis del año pasado de las huelgas y entonces eh, aquella vez no hubo oportunidad, fue relativamente corta, entonces no hubo oportunidad para aprender, pero entonces me puse esta vez con cierta dedicación. Y bueno, los traumas de un poco de salir a comprar y toda la... Ayer salí a comprar hacer el mercado y entonces, bueno, las colas y la distancia y los tapabocas y los guantes y la desinfección al entrar y la desinfección al entrar a la casa y todo eso. Sin embargo, aquí al lado hubo una fiesta anoche, me pareció rarísimo. Aquí una casa del vecindario, llegaron varios carros, hicieron su fiesta y después se fueron. Y la policía, la verdad que pasó como a las 2 horas. Me da que algunas personas no se lo toman muy en serio.
Soy surrealista y como tengo que ir a hacer compras. Sí me han comentado que en Barra tengo que hacer como que hora y media para entrar al súper y bueno,
Exacto. Sí.
¿cómo se llama? La Cruz, no, Cruz Azul, el Fibeca, que es
Ajá.
el mismo mall, no deja entrar si uno no tiene mascarilla y guantes.
Exacto, sí.
Así que,
Y hay gente buscando mascarillas por todos lados para poder hacer las compras. No las venden en los mismos sitios donde te impiden, o ya no. O sea, creo que al principio sí, yo compré las mías en los primeros días de la cuarentena, afuera de un supermercado que no dejaba entrar sin mascarilla. Entonces, este, pero hay otros que andan dando vueltas y ¿usted dónde consiguió esto? ¿Dónde consiguió? Y no. Eso, no conseguir una máscara y no poder comprar en la farmacia, ¿no? Así que,
no sé, o sea, en general para mí es preocupante por la parte que ya se ha alargado demasiado y pues,
claro,
digamos, la parte económica pues no da para tanto tiempo no
seguro,
quedarse.
sí, sí, los negocios, algunos negocios funcionan al día, ¿no? O sea,
Claro, pues todo lo de comida seguramente ya muchos de ellos va a costar que vuelvan a abrir.
claro, seguro,
Igual tiendas pequeñas. O sea, usualmente sí las de barrio he escuchado que siguen un poco abiertas y todo, pero realmente ha bajado mucho, mucho
claro, la clientela, ajá. Sí, en otros países están haciendo programas masivos. En Estados Unidos dicen que van a depositarle a la gente una cantidad a todo el mundo para, porque digamos hay mucha gente que está pidiendo beneficios de desempleo. Parece que hace un par de semanas rompieron el récord de toda la historia. 3 millones de personas pidieron seguro de desempleo en una sola semana. La gente que trabajaba en cafeterías, en restaurantes, en todas estas cosas donde se agrupa gente, ¿no?
Sí.
Cancelación de eventos.
No, acá algo preocupante también que no pasó hace muchos días fue que Confiteca, que sacaba una empresa de dulces,
¿De?
pues de dulces,
Ajá.
despidió 140 empleados,
Sí. Ajá.
así que, y no se escucha, al menos yo no escuché en la tele, está como que viendo un poco lo que, por internet, que es lo que se pusieron a hacer huelga de afuera y cosas así, pero
Claro.
más
Sí.
no se sabe
Sin
qué
mucho éxito, claro. Sí.
pues, y cosas así, pues si una empresa, si Confitec, que es una de las grandes empresas que está haciendo eso, pues no va a faltar mucho tiempo para que otras comiencen a hacerlo.
Claro, imagínate, sí, imagínate las más pequeñas que tienen menos capacidad de capear la crisis, ¿no? Sí, yo creo que aquí vienen algunas medidas fuertes de reducción de salarios y de ayuda a la gente, ¿no? De la ayuda a los pequeños y medianos empresarios. Digo, a los empleados de los pequeños y medianos empresarios.
Sí, tengo que esperar a ver qué pasa nomás.
¿Hay, hay alguno que está anotado que estaban, que es de Nano, que está ahorita presente?
Mm.
Yo cometí un error. Resulta que ahí en el Moodle hay 2 versiones del curso y no sabía para qué eran las 2 versiones. Entonces yo estaba cargando todo el material del curso en una de las versiones y entonces dejé la otra de lado. Y resulta que en la otra están anotados los estudiantes de Nano. Habían 2 estudiantes de
Sí,
Nano.
profe, disculpe, buenos días.
Buenos
Ahí
días.
somos dos, Alex Santiago Tirira y yo, Juan
Exacto.
Fernando Ponce. Lo
Ah,
que
ok.
pasa es que sí, usted nos dijo que le enviamos un correo a los de registros académicos para ver
Sí.
cómo podían solucionar eso. Nunca nos dieron respuesta desde
Ya.
la semana que comenzamos
Ah,
las videoconferencias.
ya.
Entonces no nos solucionaron nada de eso.
Ya, sí, no, entonces yo me enteré ayer, han debido inmediatamente, yo hubiera esperado un par de días nada más, si no le responden, me conectan a mí otra vez y entonces yo averiguo, yo pensé que era un error, una cosa así que se iba a resolver rápidamente, pero resulta que no sé por qué y entonces eso implica también un muy mal uso de la memoria del Moodle, ¿no? Porque yo tengo ahora y yo no he visto manera de conectar, por ejemplo, un curso con el otro de manera que no tenga que doble cargar los videos. Y yo podría, por ejemplo, también poner un link hacia la nube, por ejemplo, y redirigir todos los cursos hacia allá, ¿no? Pero ya como había cargado un montón de clases en el curso, entonces... Pero es por eso, ¿no? Porque separan a los estudiantes de nano y de física, entonces ya está arreglado, ya está todo el material ahí en el curso de nano y se pueden poner al día si fallaron, si no tenían algunas copias. Está la tarea también puesta ahí. Por cierto que hoy se vencía la tarea y no sé cuántos ya han completado esto, tienen algunas preguntas, algunas cosas que no han podido hacer o que simplemente no se han sentado, no han tenido tiempo para sentarse a hacerla. Entonces podemos dependiendo de lo que me digan hoy ustedes, ponerle una nueva fecha de entrega. Recuerden que esta es la primera evaluación, entonces sería buena bueno, que se sentaron un poco para que estableciéramos por lo menos la primera evaluación del curso.
Profe,
Sí,
yo tengo una preguntita. En este ejercicio de la densidad de estados en D dimensiones,
sí.
con los prefactors son las constantes o sea, lo que queda, las constantes que quedan en la solución final.
Los prefactors son esencialmente los prefactores geométricos de de una superficie versus un volumen, ¿no? Entonces, por ejemplo, el elemento de volumen en 3D sería 4pi k cuadrado de k, ¿ok? En dos dimensiones sería 2pi k de k, ¿ok? En D dimensiones tienes entonces, escribimos eso en clase, cuál era el prefactor que tiene que ver con una
Sí,
función gamma, y después entonces K a la D menos 1 por DK, donde D es la
ajá.
dimensión. Entonces eso es lo único que varía, ¿no? Entonces escoger el prefactor correcto asociado a la dimensionalidad del problema. ¿Ok?
Ya, o sea, entonces o sea, ahí únicamente toca ir como que haciendo o sea, mostrar cómo son los pasos para llegar a esa,
Correcto,
o
si
sea, es
lo
más o
hacen
menos lo
en
que hicimos
D,
en clases.
si lo hacen en D dimensiones de una vez, hacen todos los casos y entonces simplemente evalúan D igual 1, D igual 2, D igual 3, así, ¿no?
Ah, ya, o sea, de manera que nos queda ecuación de la densidad de estados para, para cada caso, la 3, 2 y
Exacto.
1.
Ajá.
Ah,
Y
ya.
entonces comprueban todos los prefactores que hay para una, 2 y 3 dimensiones.
Ya. Y otra pregunta más. En este ejercicio eh, del One Dimensional, pues, a ver, ¿cómo era el Crony Penny
Sí.
Model en el
Ajá.
general?
Sí.
Ahí debemos avanzar hasta una parte en la que queda esta ecuación del coseno y para
Exacto.
dar esta figura, la 8,6, ¿no?
Ajá, correcto. Sí, ahí
Ya.
para que vean precisamente cómo se resuelve una estructura de bandas, con un potencial arbitrario, ¿no? De manera que eso podría incluir, por ejemplo, el culómbico, que es el que realmente ocurre en cristales, pero también entonces un pozo cuadrado. El pozo cuadrado lo usaremos más en la parte de superestructura, de multicapas y ese tipo de cosas, donde realmente se acerca más a un potencial periódico que se puede aproximar mejor a una serie de pozos cuadrados, ¿no? Que es lo que más se utiliza en estos dispositivos multicapas. Pero también el cristal unidimensional, donde tienes entonces potenciales más genéricos. El Ashworth lo hace de manera muy general y obtiene esta ecuación autoconsistente. Realmente es una ecuación trascendente que no puede sino resolver gráficamente, ¿no? Entonces, cuando lleguen ahí se dan cuenta entonces que esto tiene todas las características del modelo sencillo que habíamos resuelto en clase del cristal unidimensional. ¿De acuerdo?
Listo.
Bueno, so let's begin in the class. If you have any other questions, please email me or ask me at the end of the class. Although today we have a meeting with all the students at 10 o'clock. So if you want to be there also, I sent the link to the student representative so that we could, anyone who wanted to join could join. Okay, so everybody see my blackboard? Yes?
Yeah.
Okay.
Yes.
Okay. Okay, so I was looking through a figure, so I wanted to do a small summary before continuing into the next our next chapter, which is going to be carrier transport. Okay, so just a brief summary here, and I think I chose the figures that sort of comprises the whole scenario that we have been looking at in the equilibrium case. Okay, so remember this figure. So we have the valence and conduction bands. Okay, so this is the scenario including including the fact that we can have impurities in the problem. So here we have the energy axis. So this is the energy. Okay, we have the conduction band, the valence band. Okay, and so now we could have, for example, in the non-degenerate limit, which is the dilute impurity limit, we can have a series of levels close, okay, to the conduction band. Okay, we saw a very simple theory of why these levels are going to be close to the conduction band. This has to do with the ease of ionizing electrons from, for example, donors. So these are donor levels, okay, donor levels. And then we could also have impurity, other types of dopants, which have one less electron than the matrix in which you put. So, for example, the donor levels could be something like having silicon as a matrix and then phosphor, okay, as a dopant. And here we could have silicon as a matrix and boron as a dopant. Okay, so these would be examples. Okay. The phosphor has one more electron than the silicon, so it's a donor. It can donate that electron, and we have to ionize that electron. So this would be the gap here would be the energy to ionize that electron. And boron has one less electron than silicon, so it essentially builds in a hole into the matrix of silicon, and then electrons can go from the valence band to occupy those holes, creating a positive carrier in the valence band. Okay, so so these are the donor levels here. Okay, and these are they're called acceptors. Okay, acceptor and donor. So these are the two types of impurities we're going to have. Okay, generally by and this type of doping occurs randomly. Okay, so these are random impurities in the lattice. Okay, and the most common ones are the substitutional, what they're called substitutional impurities. Okay, substitutional means that boron is taking up the space of a former silicon atom that used to be there, and phosphor is doing the same thing. Okay, so that's a substitutional impurity. Substitutional. Very long word, that one. Let me make some more space. Okay, so so the next story. Okay, so this is just a story of the spectrum associated, but then we also address the occupation. So some of these donors can be ionized here, the same as these can be also occupied by additional electron. We also call this ionized because this is creating a negative ion here, and this is creating a positive ion. And so associated with these ionizations, we will have carriers in the conduction band here, and we would have holes associated with those. Okay? We also have the case where some of these ionized donors can dope, put it here. So some of these ionized donors can occupy acceptor levels. So we could have negative signs associated with those. So that's part of the scenarios that can occur. We can either ionize the electrons here in the donors and send them to the conduction band, but then we could also ionize some of these and they go to occupy the acceptor level. So none of these two produces either a carrier in the conduction band or a carrier in the valence band. Okay, and then you have, so this will be the ionized donors, the ionized impurities. Okay, and then we could have a set of unionized. Okay, so not all of them need to be ionized. This is a function of temperature, of course. At room temperature, for example, all these impurities tend to be ionized because there's such a small energy scale. This donor, the difference between donor and the conduction band and the donor level is much less than kBt. Okay, so these tend to all be ionized here, and these tend to be all occupied, but some are going to be not ionized. Okay, so they stay. So these are neutral levels that are going to be here. Okay, that are going to be inactive, but we always have, no matter how small the temperature, we're going to have some holes here that are going to be generated by just thermal excitation. So we're going to have these things. So these are because there are electrons that jump the whole gap. Okay. So this will be intrinsic carriers. Okay, and these are also intrinsic. Okay, so we derived last class the whole how then we build for the whole concentration of negative carriers in the conduction band and the global. Okay, so this is the total concentration, okay, of electrons, and this is the total concentration of holes. Okay, so we derive expressions for these, and we start from the condition that we have we have a restriction, okay, or condition restriction that overall charge neutrality. Okay, remember that all the atoms going in to build the crystal are neutral. They have as many electrons as they have protons in their atoms. So all the atoms that are coming in to build this solid are going to be neutral. And then the charge separates once you build these, for example, phosphor into silicon or boron into silicon. They separate their charges and then they contribute to carriers either in the conduction or the valence band, okay? But the sum of all these charges have to obey the neutrality condition, and I'll just put that one just to remind you. So the neutrality condition, okay, this is like a conservation condition. Condition. Okay, this is like conservation of energy, conservation of momentum. This is conservation of charge. Okay, conservation of charge. So you start with 0 and you need to end up with 0 also. Okay, so we have that the total amount of negative charge in the conduction band plus, okay, the number of negative acceptors, which has also the ionized acceptors. So this is the total amount of negative charge, okay, has to be equal to the total number or the density of positive charges in the valence band plus the number of donors which are ionized also. So this is the number of positive charges. Okay? Okay, so these need to be equal. So this is the condition for neutrality. Okay? You start out with zero net charge, you end up with 0 net charge, no matter the distribution of who's ionized, who isn't, and all this, and even the contribution from the intrinsic carriers. So this, if you follow the last class, we derived 2 expressions, one for the total amount of negative charge in the conduction band, okay, from any source, that is from either intrinsic or extrinsic sources, okay, either from the silicon in the case that we always mention, or the impurities, be they acceptors or donors. So we have this expression here, okay. It's okay. 4 plus. And then we have also the expression for the total density of positive charges in the valence band, and this just switched these 2 variables here, plus. I'm just going to keep the order here, although it doesn't matter, just so that it can be more memorable for you. Okay, so this is the total concentration, and we have to remember that this is always done in the Maxwell-Boltzmann limit, or Maxwell-Boltzmann approximation. That is, we take always that the distribution function in the valence and the conduction bands are going to be mostly Maxwell-Boltzmann and not Fermi-Dirac. So we use also the relationship, which is very important to remember, that once you have one of these concentrations, from the practical point of view, it's better to use calculate the other concentration by using this Maxwell-Boltzmann relationship between one and the other. Okay, so this, once you know one of these concentrations from this formula, the other concentration we calculate through here. Generally, we have a n-type, so we depending on which one of these. So if n0 is much larger than p0, we have n-type semiconductors. Okay, and if it's the other way around, then we have p-type. Okay, so generally one is going to have one or the other. Okay, and the fact that we have both N0 and P0 is due to what is called compensation. Okay, compensation. And compensation is having both types of carriers, okay? One majority, one minority. And in the limit that we have both are the same, although this may not be the best case scenario for a particular application. These are completely compensated, completely compensated. Okay? Okay, so this is sort of a summary. Okay, we derived a few other things related to different temperature regimes, for example, associated with the occupation of these levels. Okay, and certain relationships between the energy references Fermi energy and the with respect to the intrinsic Fermi energy related to the densities in the conduction band and in the valence band related to the intrinsic concentrations. Okay, so so if you want to review any of this, or if you have any questions related to this, please ask. Okay, but the videos are posted in the Moodle. Okay, any questions about this? So this is the sort of the full scenario that we have to address now. Now, in this next section that we're going to do is to now address the motion of these carriers here that we have either in the conduction or the valence band. We're going to consider, and that's a very good approximation, that these charges here are not going to be mobile, so these are just ionized donors and acceptors. Okay, so these charges are going to stay put. Okay, but we can have transfers between the valence of the conduction band, so we're going to be able to change, for example, in non-equilibrium situations when we have an applied external voltage, that the carrier's concentrations can change. Okay, so we can either occupy more these donor and acceptor levels, and we can change the concentrations in these the valence and the conduction band. Okay, so that's what where we're going from this chapter on. So we're going to address now carrier transport. Okay, so this is going to be a series of very simple relationships, but very significant relationships of how carriers move. Okay, and I'm just going to make an additional comment here, which is this is close to equilibrium. Okay, so what we're going to address here is just carrier transport that doesn't affect the equilibrium conditions. Okay, because the next chapter we're going to go far from equilibrium. Okay, as opposed to far from equilibrium, which is going to be the next chapter. Okay, so I'm sure many of the things we're going to say here are very, very simple. You've seen them before, but we have to review them and introduce some new concepts, which are sort of concepts that are very frequently used in this topic. So first, imagine we apply an electric field. So let me sort of draw for you the scenario. We apply a certain electric field here, okay, and we have our block of material. Okay, so this would be an external field applied. We have a block of material, and we have some carriers associated with the either the conduction band or the valence band. Okay, so these are going to be quasi-free electrons, because remember that the dispersion in the vicinity of of the bottom of the conduction band, of the top of the valence band, is going to be free electron, okay? So if we have a negative charge here, okay, we have a negative charge here, this electron is going to respond to this electric field moving, okay? So it's going to be subject to a force, and the force is going to be let me put a more generic thing. So we have, it's going to be the electric charge times the electric field, okay? So depending on the value of this charge, this could be, if it's 4 electrons, okay, this is going to be minus E times the electric field. And if it's for holes, it's going to be plus E, okay? So you see that the force acting on a negative charge is going to move it then opposite in the opposite direction to the electric field, while if you have a positive charge, which I'm going to put like this, but you know this is a hole, this is a missing electron, it's going to move in the direction of the electric field, okay? So this is intuitive what's going to happen. In the valence band, we're going to have carriers moving in the same direction as the electric fields. Let me put, this is not energy, but electric field. Okay, and the electrons are going to move opposite in opposite directions. But you know, and this we will calculate explicitly, this electric field is going to generate a current in this direction. We're going to denote the current, okay, like this, and we're going to call this acceleration, the drift current, okay, drift current. Okay, I don't know if you've heard this term drift. Sometimes when you have a window open and you feel, oh, it's cold. There's a drift coming through the window. This is a sort of a macroscopic current of air at the outside temperature that's coming into the house. Okay, so this is the origin of this term. This is a drift, sort of a small current. Okay, small current or something, or a small flux. Okay, this is why we use this term here. So drift current, this is a drift of charge. Okay, so both when electrons are moving in the negative direction, so this is a positive and negative direction. Okay, so when electrons are moving in the negative direction, because they have this negative charge, they produce a current in the positive direction. And of course, the motion of the positive carriers moving in the right direction, on the positive direction, are generating a current in the same direction. So both of these motions produce a current in the same direction. And we're going to derive this explicitly, okay? So any questions about this? I guess this is very familiar to you. From the common core physics or the basic electricity and magnetism that you learned a little while ago. So this is the first contribution we're going to derive. So we're going to have, for example, the electron drift current. Let me sort of denote it like this. Maybe not. Let me change this notation, because we're going to use, instead of E, we're going to use N here. Okay, so negative contribution. So you have here some density. Okay, this is going to be the density of carriers. Okay, times some drift velocity. Okay. And this is the drift velocity. Okay, there's one thing that we're forgetting always here, that this is the sort of the zero temperature scenario. Okay, so this would be 0, so that the electrons, from the puristic point of view, will not have no thermal fluctuations. Okay, so the electrons just will have the drift velocity and no other sources of motion. But we know that when t is different from 0, we will have also thermal motion. Okay, so the electron, when we have no applied electric field, and let me draw thermal motion. So what's the scenario there? So if we have thermal motion, then on top of the drift, so this will be the sort of the zero electric field case, we have that the electrons are just moving about, receiving kicks from the temperature reservoir, okay, and moving around like this. Each of these vertices here are kicks by the thermal reservoir, and they're moving around like this. So when we have E different from 0, then of course we have now the thermal motion, but it's going to be moving in a certain direction, okay? Okay, so this will be the thermal motion, and on top of it, it's going to have drift. So we're going to have both thermal velocities, okay, and we're going to have drift contribution. Here we only have thermal. Okay, so in a few minutes we're going to see the relationship between these velocities here, these thermal velocities here, and each of these branches here, compared to the drift velocity. So this will be the drift velocity moving in a certain direction. Okay, and these here will be the thermal contributions. Okay, so this is sort of the physical scenario for the velocities that we are going to be considering. Okay, any questions? Okay, so let us derive now what the physical picture for this expression I just wrote for the current density. Okay, so again, we have the drift contribution. So we have the negative drift contribution, and this is going to be a charge density, okay, times a drift velocity, okay? So what's behind this? First, let's see what the dimensions. So dimensions. Notice that this is a charge, okay? So this is a Coulomb per unit volume. So cubic centimeters times a distance, okay? So this is going to be centimeters, okay, over time, seconds. Okay, so here we're going to cancel a factor here, and we leave this factor in 2, so this is going to be Coulomb area seconds. That's going to be the units of the drift current. It's called the current density. Current density. Okay, that's coming from this per unit volume associated with a charge. Okay, with the charge density here, and the dimensions are going to be coulombs over area seconds. Okay, so where does this come from? This is coming from the following. So we have, let's imagine a block of material, okay, You must remember this from solid state 1, at least. You have your block of material here. Okay, and this is going to be the cross section. So you're going to see the motion of electrons perpendicular to this surface. So this surface has area A, and there's a density of electrons here. So we have this here is going to be delta L, for example. Okay, and this delta L that I draw here is going to be related to the drift velocity of these electrons times a certain delta t. So this is going to be the distance run by the electrons that are included in this block in this time if we have this drift velocity. So all the electrons that are contained in this block are going to go through this surface area A in time dt. So this is why I chose this delta L. Okay, so if we have the total charge, okay, so total charge that is going to be transported, okay, through A is going to be the density, okay, the number of electrons per unit volume, okay, or the charge per unit volume, times delta L, okay. So this will be the total charge per unit volume, and it will multiply delta L times A. This is this times this area is the total volume. So this is the number of charges, okay, and divide by delta T, okay? So this is the number of charges per unit volume, okay, that are going to be transported there. So if we translate now this through this relationship, delta L over delta T, this is going to be then rho times the velocity, okay, times drift velocity times the area, okay? So this is total charge, okay? And if we divide now the total charge per unit time, okay, then we divide both sides by A, okay, so we get, let me just put that explicitly, by A, then we get the definition, okay, area and time, okay, then we get the definition of our current density. So our current density is going to be here, okay? So this is the meaning of this current density. In this case, it could be positive depending on how I choose this density here. It could be either of electrons, okay? So this density could be electrons or holes, okay? Is this clear? This is a very simple derivation. This is a common core derivation of the current. And this is enough for us. Okay? So this is going to be the drift current. Any questions? Is it clear? Okay. Another derivation we did in solid state 1 is one that defines another derivation. This comes from solid state 1. Okay, is the conductivity concept. Okay, so this is what we call always, and you should remember this as a very important reference model, the Drude model. Okay, and this is a sort of the classical picture. It doesn't take into account quantum mechanics. But then from quantum mechanics, it turns out that this is a very good model if we incorporate the quantum mechanics into the definition of velocities and masses, okay? So the quantum mechanics, okay, it goes to quantum mechanics by reinterpreting the mass as the effective mass and the velocities using band theory. Okay, so this is how we complement the Duder model. If we redefine mass and velocity using quantum mechanics, then we get a very good description of the physics inside a crystal. So what is a Drude model? The Drude model just says that mass times the derivative of the velocity with respect to time is going to be, on the one hand, the effect of the force exerted. So this is going to be mass times acceleration. So this is force. One of the sources is going to be, for example, the electric field. And then we're going to have a phenomenological term, which is a source of friction that you have in the solid, in the material. So the phenomenological term, okay, phenomenology, and the times of Drude, he imagined that, you know, this is a kind of a friction, okay, friction that the electron feels inside the crystal, and in principle does not allow this electric field to get out of hand. Okay, this means that if we eliminate this term and solve this equation without this friction term, then the electron accelerates and accelerates and accelerates forever, right? And we know that this doesn't happen in a solid, so there must be some kind of a friction term that opposes the acceleration of the electric field. So we need to put this one in. And the main things that I've input here is that we have now the mass, okay, which can be interpreted quantum mechanically eventually, and also the this is the collision time. Okay, which, as we will see, is going to be related to a mobility, which is a concept that Einstein actually introduced into this subject. Okay, so this is going to be a collision time, and there's no at this level there's no other way to determine these things but determine them from experiments. So this is why this is called phenomenology. You go to experiments and you find something that behaves in this way. So this is a sort of a model of what's going on. And you calculate from this the transport mass and the collision time. So these are parameters of the transport model. Okay, so how do we approach? How did we approach the solution of this equation? We just said, okay, stationary solution. That means a solution independent of time. So we set the left-hand side to 0. We say 0 is equal to, there's no change in time, equals to a balance between the electric field and the frictional term. Okay, so if you solve now for the velocity, you get that m times mv over tau is equal to E times E. Let me draw my E more nicely here, okay? And this implies that the velocity is then E times tau over m. Okay, so this will be now the sort of the stationary velocity, which is a balance between the electric field and the friction. Okay, so this you see we reached it. Depending, this is going to be a fixed time between collisions that depends on the impurity density and the types of impurities we have. So we may have many sources of collisions, and we're going to see how we compound these sources of collisions in semiconductors. And then it's related to the mass, okay, to the effective mass, okay, of the carriers. If the carriers are heavier, then the velocities due to the same field are smaller, okay. If the masses are lighter, then we can the electrons will have more, or the carriers are going to have more speed, okay? And we know this effective mass varies from one band structure to another. And then if we have a very long collision time, okay, so we have very few impurities, then this tau is very long, so the velocity is high. And if we have lots of impurities in our problem, this is going to be short, so the velocity is going to be slower. It's going to have much more scattering, okay? So this formula makes perfect sense. If we have larger charges, we have larger velocities. If we have larger electric fields, of course, we're going to have larger velocities and so on, okay? So let's now introduce this into the concept of current density. Any questions about this view graph? Okay, so now let's remember that we said that the current density is going to be velocity, density times velocity. So density times velocity, whatever the density is, whether it's, this is going to be, let's decompose this. For example, in the case of electrons, it's going to be the electron charge times either the negative density or the electron charge, the positive density in the case of the valence band. So this is going to be valence, okay? And this is going to be conduction, okay? Going to put in here, I'm not mentioning the sign of the charge yet, so this is going to be, and this is the number density of carriers, okay? Same here, number density. So number density times the charge is going to be the charge density, okay? So we multiply now this charge density by that. So we're going to have, for example, in the case of the electrons in the conduction band, we're going to have E times the charge density, and then we're going to have the velocities. So the velocity now we substitute for the previous relationship. So we have E times the charge density times tau over m times the electric field. Sorry. So this is rho, this E times N, and we have another factor of E. So remember here, we have here, V is E times E, so we E times tau over M, okay? Let me write it more clearly here. So we have E times N, and then we have E times tau over M times the electric field, okay? So this is the velocity, and then we have E squared tau over M times E. Okay? So this is the form, right? So every time you have a current, and this current is proportional to some driving force, which is generally written as the gradient of something, okay? For example, the gradient of the potential is going to be the electric field, okay? So the coefficient, okay, there's a coefficient here that is not, okay, that is not included in this relationship. Okay, it's going to be a transport coefficient. Okay, so in this case, here we have the proportionality between the current density and the electric field, and this coefficient is going to be called the conductivity. Okay, and this happens for many things. For example, also if you have, this is charge current, so charges are moved by gradients of the potential, but we could also have, okay, example, simply gracia, thermal current density, okay? This is going to be something proportional to the gradient of temperature, okay? And this is going to be the thermal conductivity, okay? And in this way, you could define all the transport coefficients, which are always linear in the gradient of something, okay? This is the gradient of the potential, the gradient of temperature drives the heat currents, okay? So this will be heat currents. Any questions? Okay, so these are going to be, these prefactors are going to be transport coefficients. In this case, the electrical conductivity, and this is going to be the thermal conductivity. Okay, so both of these gradients generate currents inside the semiconductor. Okay, so this is a very important relationship. Okay, you saw it before in solid state 1. So N, this is the number density of carriers or negative carriers in this case, E squared, the collision time over the transport mass is equal to the conductivity. Again, this has all the usual features that we should find in the conductivity. If the mass of the carriers is large, the conductivity is small. If the collision time is small, we get a small conductivity. That means we have lots of impurities, so we have lots of drag in the intuition of the classical intuition, okay? And if this tau is very large, then we have very dilute impurities, so the electron can be accelerated a lot by the electric field, so we have a larger conductivity, and we also have the dependence on the carrier density. If we have more carriers, we have more conductivity. So this has all the intuitive features of a conductivity. Remember that this is an intrinsic quantity. That means that it depends on the material, but not on the geometry. Okay, does not depend on geometry. Okay, so this will define later. Okay, later we'll define, instead of conductivity, conductance. Okay, and resistance, which is going to depend. These two quantities depend on geometry, but this is an intrinsic. Okay, so we have a piece of silicon. It will have an intrinsic conductivity, no matter what the geometry of the silicon is. But when we stick, cables to our system, then we have to take into account where we stick the cables and what is the geometry of the system, and we determine experimentally. We determine is these quantities and not this quantity here. Okay, we can, of course, once we have these quantities and we eliminate the geometrical factors, we obtain these intrinsic quantities here. Okay, any questions? Okay, so let's continue. Okay, so now we introduce a new concept. Okay, it may be more useful in some circumstances than the other. It's historical, since instead of using the conductivity for everything, we can use mobility, which is more or less the same concept. Okay, but it's just very much used in the field of semiconductors, so we should introduce it also. So now we have the drift current. Okay, a positive carrier drift current. Okay, and the definition of mobility is just that this is going to be the positive mobility, the mobility of the positive carriers times the electric field. Okay, this is sort of the definition of mu here. Okay, and we also have the velocity of the negative drift current. Okay, is going to be defined as mu n here. Okay, so let me introduce now the correct sign. So the negative is going to have, again, because this is the relationship between the electric field and the velocities, we know that the velocities generated by applying this electric field to negative carriers is going to have this minus sign, and to positive carriers it's going to have this sign. Okay, so now we'll be consistent with the signs here. Okay, so let's put now the drift current. Okay, so the positive drift current, drift, is going to be E times P. This we said that this was the charge density, this product, times the drift current of positive carriers here. Okay, and now we use this relationship here, so we put this in terms of the mobility. It will be E times P times the mobility of positive carriers times the electric field. Okay, and the same here for negative drift. Okay, the negative drift, then we're going to have that this is going to be minus. Okay, now putting in the corresponding density, charge density, we're going to have minus E times the negative density, number density, times the negative drift velocity. And now we substitute this and see how we get a current in the same direction. Okay, let me just spell it out here. So we have E times N, and then we have mu and D is going to have minus mu N times the electric field. Okay, and so this is going to be E times N times mu for the negative charges times the electric field. Okay, so you see that both of them are going to be positive current because of this double negative signs here. Either the definition where the electric field moves the electrons in the negative direction, and then we have the effect of the negative charge. So both contributions are going to give us a positive current. Okay, positive, or a current, let me say a little more precisely, current in direction of the electric field. Okay, is it clear how we derive this? So this will be important. Again, I draw the picture I drew a little while ago. So we have the electric field applied in this direction. Okay, so we know that the positive charges are going to move in the direction of the field, and the negative charges are going to move in the opposite direction. But when you calculate the current density, you have to go through this process, taking into account the fact that the carriers are negative, and the fact that you're moving them in the negative direction. So both of these negative signs cancel, and you get a positive. So both of them produce a current. Let's put it like this: P, a drift current that is in the same direction. Okay, important. Okay, you should remember this charge, this negative sign cancellation here. So both of these currents. So imagine that you have now a semiconductor. Okay, let's draw it in the band picture. So you have negative charges here. You have positive charges here. This will be very important in analyzing when we see, for example, the PN junction. So we apply an electric field in this direction. Okay, so we know that these charges are going to move in this direction. These charges are going to move here, and this all produces positive current. All produces current in E direction. Okay. This fact can also be seen physically in the following way, and this is useful, you know, to a useful way to generalize this this concept of charges or any quantity moving in a certain direction. Notice that if you move electrons, okay, let me put here intuition. Okay, if you're moving negative charges in this direction, you're generating positive charges here. You're taking away, okay? You're taking away a negative charges in this direction, so you accumulate, okay? Accumulate positive charges in this place. And this is the same that is done by moving positive charges in this, is accumulating positive charges here. Okay, this concept intuition can be applied also to spin. For example, when you have either moving spin in one direction and the other, you can see it as an injection of spin or taking away the opposite spin. So we also inject the same sign of spin in that case. This is the charge version of that argument. Okay. Any questions? Okay, so let's summarize. Let's summarize here the sort of the drift current. So we have the drift current due to all. Okay, let me put due to all carriers. Okay, it's going to be the electron charge. Okay, which is going to be either the charge associated with the electrons in the conduction band or the holes in the valence band. So it's going to be a combination of the negative charge mobility, okay, times the density of negative charges, positive charge mobility times the density of positive charges times the electric field. Okay. So let's compare this now, a connection to conductivity. Okay. So on the one hand, for example, now we take the particular case of a P drift current density, and this is defined by positive, emphasize positive, times the positive mobility, positive carrier mobility, times the density, times the electric field. And on the other hand, this was the number density of positive carriers times E squared times tau over M times E. So from here, you see that if you compare these two expressions, and you know that this is the conductivity, okay, you can compare these two expressions and you get an expression for the mobility of positive charges. So this equals to this. These two P cancel, and we get, and the one charge cancels from here, and we get, then this is proportional to the charge to the time, scattering time, and the effective mass. Okay, let us always put here the effective mass because this makes a connection to quantum mechanics. Okay, so this is the transport effective mass. Okay, we've mentioned the effective mass before, an effective mass that comes from the band structure. Okay, so we're going to have a bunch, there's going to be a bunch of effective masses. For example, the density of states effective mass. Okay, so effective masses. Put a separation here. Effective masses. So we're going to have depending on how we measure this mass, we're going to give them different names. So this is the density of states that we had seen before, it's related to the band structure only, okay? Band curvatures, okay? Then we're going to have the transport effective mass. Effective mass, okay, which is this one associated with the transport measurements, okay? And for example, another one we're going to see is the cyclotron. Effective mass, okay, which is related to how electrons move in a magnetic field, in magnetic field. Okay, so we're going to have a bunch of those depending on what experimental technique we use to measure this mass. Okay, for example, an example of the density of states effective mass that we had seen before. Example. So you really make connections now. Remember that the free electron effective mass came from drawing kx, ky, kz. Remember, so this is the reciprocal space. So we have these three. So the free electron dispersion in this space, okay, in 3D. How was it drawn? We drew a sphere here, and this is how electrons are going to behave far from the edges of the brilliant zone. Okay, far from edge of brilliant zone. So you know that if you're close to the edge of the brilliant zone, then this sphere gets deformed into a very complex structure. But far from the edge, okay, then we get a spherical dispersion. What does this mean? That the energy of the electrons are related to their momentum through a sphere, the equation of a sphere. So what's the equation of a sphere? Okay, this plus y plus kz. Okay, and if this is going to be a sphere, these masses have to be the same because these coefficients have to be the same. We know h is the same all over the place. Okay, these coefficients, okay, same mass in all directions. Okay, this means that if I try to accelerate an electron in the y direction, it will respond in the same way as an electron moving in the x direction, the same as an electron moving in the z direction. Okay, so that's what this spherical dispersion means. Okay, but now let's do the real case. So what happens to silicon? Okay, so this happens only in the vicinity of a free electron gas. Okay, this will be a free electron gas. Where the electrons have, they don't have any obstacles. Okay, there's no crystal, so just a box filled with electrons, and we have this dispersion. Or when we're very far from the edge. Okay, but we know that silicon has a more complicated dispersion, and this would be the conduction band of silicon. Conduction band of silicon. Then we have this very strange dispersion here. okay? Instead of having a spherical thing like this, we have pockets. And you must remember, I mean, these are the most exciting drawings you can do in solid state 1. You derive things like this, the silicon. So these are the electrons, the pockets of electrons in the conduction band. Okay, so this is exactly the same as we had before. Kx, Ky, Kz. Okay, so if we accelerate the electron now in any direction, we have to see, for example, what is going on with here. So let's focus on this pocket. Okay, so we draw the axis there again. Okay, and we're going to have an ellipsoid instead of a sphere. Okay, ellipsoid. So, and this is the Kx, Ky, and Kz directions. Okay, just refer to this point. This would be the center point here. Okay, so if we have an ellipsoid, what is the equation now? The equation is going to have an effective mass in each direction. So if you accelerate in the direction Kz, is going to be easier than if you try to accelerate in the xy direction, because the effective masses in each directions are going to be different. But now, let me just draw the two components. Okay, so we have now going to have an effective mass that depends on the direction. So we have to draw x, okay, and Ky, my plus, okay, the rest of the term. So we're going to have a different effective mass, and this is the equation of an ellipsoid, okay? So these pockets, we're going to have to describe at least the effective mass, the d density of states, okay, effective mass, okay, are going to be derived from the band structure, okay? Band structure. Okay? Is this clear? Any questions? No? Yes? Anybody there?
Yeah.
Okay, you're there, okay. Okay. Okay, so we could review, you know, how you get these pockets a little bit in solid state 1, but I guess you remember them very well because these were these very, very nice Harrison pictures you generated, at least in the two-dimensional case, where you derive these pockets very easily. Okay, these pockets can be drawn very easily. Okay, so this is the effective mass you will get from just the band structure, but then you can do electrical measurements and measure the effective mass of the electron through these relations, and then you call them, instead of the density of states effective mass, you call them transport effective mass. So remember this notation so that you know that it's just the effective mass derived from different techniques. Okay? So let's end the class by talking a little bit about temperature dependence. Okay, so this we're not going to be deriving any of the results, because these are, in general, they're very difficult to derive theoretically. So you have to really go into very sophisticated techniques to derive from theory what the temperature dependencies are. So we're going to only use phenomenological arguments in this case, okay? Phenomenology. In this sense, we behave a little bit like chemists, okay? So, so again, we're going to have various contributions to the mobility, okay? Various temperature dependence from the mobility, depending on what physical factors are limiting the mobility, okay? So, for example, we're going to have the mobility associated or mobility limited by lattice fluctuations, lattice thermal fluctuations. Okay, and this is known experimentally to be proportional to a power law like this, minus m. Okay, where this can be any number, not an integer. Okay, this is typically a fraction. So, for example, certain theories predict that this is going to be 3/2. Okay, theory. Although in experiment, it doesn't go like this. It goes like an inverse the power law of temperature, but not 3/2. Okay. So what does this mean? So you have your lattice. Okay. So these are the ions left behind by the electrons. So you're trying to move electrons. For example, this is silicon, and we have negative charges trying to move through this. Okay, so if these ions do not move at all, then your mobility will be high because the electron can just move through these things and it doesn't encounter any impurities and things like this. But if you apply a finite temperature, if temperature is different from 0, then these ions are going to move around. They're going to oscillate. Okay? So if they oscillate, they're going to interfere with the electron motion in any particular direction. So you're going to get sources, okay? Sources, thermal motion. Okay? Is going to be a source of scattering. So they will behave essentially as having like impurities. Okay, like objects that are in the way or larger substitutional impurities that may exist here that are going to interfere with the electron motion. So typically as we lower the temperature, okay, so this is an inverse dependence here. As we lower the temperature, then this is going to be larger, okay, and the mobility gets large as we lower the temperature. So this is why we have this inverse dependence on temperature. As we lower the temperature, the fluctuations disappear and the mobility goes up. If we increase the temperature, this becomes small, okay? This means there's lots of fluctuations, lots of interference with the electron motion, and the mobility gets reduced, okay? So this is the first source of temperature dependence. Okay, and then we also have impurity scattering. Okay, and this can be very important. Impurity scattering is going to be very important in semiconductors because you have all these donors and acceptors lying around which are ionized. Okay, donors plus acceptors ionized. So this means that these are going to be a very strong source of scattering because there's going to be a Coulomb interaction between the carrier and the impurity. So you have now the same scenario as before. We have the silicon atoms, and now they can have, the impurities can have charges associated with them because they've been ionized. So when an electron comes, okay, then it sees a Coulomb potential due to the impurity, and it gets scattered. Okay, it gets scattered like this, scattering. Okay, so the mobility the limited mobility due to impurities is going to go like T to the 3/2, okay? And this is again phenomenological, okay? Measured in experiment. So this is going to be a power law, and it's going to be inversely proportional to the number of ionized donors and number of ionized acceptors. Okay, so these are kind of phenomenological rules that you should have in mind. Okay, so we're not going to derive these expressions here. This is involves a more sophisticated theory. But you see here that now the temperature dependence is a positive. Okay, so this means that another phenomenon is happening, that if you have a lattice which has lots of these ionized impurities and the lattice is static, then this scattering is very effective, okay? But if these impurities are now moving around, this sort of makes fuzzy the effect of the Coulomb interaction. It sort of distributes its inner volume, okay? And this scattering becomes less effective. So as you increase the temperature, then this scattering becomes less effective, so the mobility increases, okay? The scattering is reduced, it's sort of smudged over a region instead of being concentrated and generated a point scattering phenomenon, okay? So this behaves in the opposite direction as the temperature dependence. So as fluctuations increase, the temperature increases, the lattice source of mobility is increasing, while the impurity source of scattering is getting reduced. Okay, so these are opposite. Okay, so let me see if I can draw this opposite effects. Okay. Okay, so the last thing I'm going to say, you have to go to another class, so let's stop here. Okay, so so we will continue next time to see how then the scattering times associated with lattice scattering and impurity scattering can be now combined into a new effective scattering time that we will use then in all the expressions we derived before. Okay, any questions? Okay, remember to tell me about your, if you have any questions about the homework, so we can, you know, I will establish a new date for the homework. So let's suppose, let's say, for now, decide homework due, this is a second due date, next Thursday. Okay, so try to work at it. It's a very simple homework set so that we can establish our first evaluation.
Profe, ¿la tarea se la entrega por correo o en el Moodle?
La verdad es que no estoy enterado cómo se entrega por Moodle, pero yo preferiría que me la mandaran por correo electrónico, así queda más bajo control de Gmail en vez de Moodle. ¿Ok?
Porque
Sí.
en Moodle sí aparece la opción de cómo, o sea, aparece la notificación y cómo enviarla.
Ok.
Y no, o sea, no sé si le, o sea, yo le había enviado la mía, pero no sé si llegó o no.
¿Ya habías enviado la tuya?
Sí, o
Ajá.
sea,
No, déjame chequear. Vi una tarea hoy, pero un correo referente a la tarea, pero era alguien, un estudiante pidiendo una extensión para la fecha. O sea que vamos en principio a establecerla, porque lo que pasa es que yo voy a entregar soluciones. Entonces, si entrego las soluciones, obviamente le doy, si alguien se retrasa, entonces no puedo entregar la solución hasta el miércoles, el jueves que viene, ¿ok?
Ya.
¿De acuerdo? Entonces, hagamos eso por esta vez y después entonces, bueno, ya como establezcamos el tempo del curso, entonces sé para cuándo pedir la segunda tarea y así sucesivamente. Sin embargo, me voy a dar la libertad de este fin de semana les pongo la segunda tarea en el Moodle para que los que vayan un poco más adelantados tengan entonces ya el chance de ver los ejercicios de la segunda parte del curso. ¿Ok? Chévere. Bueno,
Profe,
sí,
una preguntita rápida. En esta fórmula del ejercicio final, similar al Cron y Penny general,
sí,
por ejemplo, ahí queda en la ecuación al final en el denominador el t, el valor absoluto de este coeficiente. Este coeficiente está relacionado con, o sea, es el de transmisión, pero en los valores para ponerlo o sea, para graficarlo, tiene que estar relacionado con este K, el mayúscula, en lugar del wave vector.
sí, sí, pero tú dices para un valor específico, tú dices para hacer un plotting.
Sí,
Ajá. Sí, ahí, claro, como ese problema está resuelto para un potencial genérico, entonces tú tendrías que meter esos valores con la mano, ¿no? Entonces simplemente usa, obviamente que este valor está limitado por 1 máximo, entonces puedes poner un valor de penetración de la barrera para asignarle un valor a ese parámetro ahí, ¿no?
ya. Y luego también, no, ya. Claro, eso va a estar siempre entre
Claro, porque eso depende
0 y
si
1.
qué tipo de
Ya,
barrera escogiste, va a tener más o menos transmisión, entonces
ya,
eso
listo.
te va a influir sobre el ancho de la banda que obtienes, ¿no? Eso te va a
Ajá,
determinar el ancho de banda que tienes. ¿Ok?
ya, listo.
Chévere. Bueno, entonces nos vemos mañana. Y bueno, y si quieren asistir a la reunión que hay, espero que tengan el link, si no, si ya tienen claro las cosas que se van a discutir ahí. Yo creo que más que todo, los representantes estudiantiles quieren tener una visión clara de cómo estamos planificando las cosas durante este periodo. ¿Ok? Bueno, nos vemos mañana entonces. Hasta luego.
Hasta luego, profe, gracias.
Hasta luego.